Hey, you're back. This time we're to chapter 2, doing problem number 1. Rather long-winded here. A small probe is exploring a spherical asteroid. As the probe creeps over the surface, it drills holes to take soil samples. Scientists on Earth notice that the sun shines straight down into one of the holes at the same time, 10 kilometers due north of the shadow of the the shadow of the vertical antenna on the main landing craft allows the scientists to deduce that the sun is 15 degrees from directly overhead. What is the radius of the asteroid? This, of course, is designed to be very much the same as the famous Eratosthenes experiment for measuring the size of the Earth. The geometry is the same thing that we saw in class and in the textbook. There's a hole drilled into the asteroid, and the sunlight is going perfectly straight down into that hole. But further north, there's an antenna sticking straight up, but the sunlight there is casting a shadow. These are parallel rays of sunlight because the sun's so very far away. And it's the curvature of the asteroid that's causing the vertical directions to be different at the different places. We can set up the geometry. If we continued this hole downwards, we'd reach the center of the asteroid. If we took this vertical pole and went downwards, also that would be the center of the asteroid. We were told the distance between those two was 10 kilometers, and the shadow being cast here was found to be 15 degrees. Because this line is parallel to that one, we can use the rule of alternate interior angles. This is a diagonal across two parallel lines. This also has to be 15 degrees. Our goal is to figure out the entire circumference of the asteroid, and then we'll use that to get the radius. We set up proportions. This 15 degrees of angle here is just a fraction of the whole complete circle of 360 degrees, but we reason that should be the same fraction that the 10 kilometer distance is of the entire circumference, which we'll call C. We can solve for C by, when one fraction equals another, you can cross multiply. We can do it that way. So 15 degrees times C would be equal to 360 degrees times 10 kilometers. To solve for C, I want to divide both sides by 15 degrees. 15 degrees cancels there. So C equals this. The degrees are a unit. Those cancel. 360 times 10 divided by 15 gives us C equals 240 kilometers. The problem asks for the radius of the asteroid. And as you've been taught in the past, I know you have, the circumference of a circle or a sphere is 2 times pi times the radius of that circle. So the radius is the circumference divided by 2 pi. Here we do 240 kilometers divided by 2 and divided by pi. Make sure on your calculator that you do divided by 2 and divided by pi, or divided by parentheses, 2 times pi, close parentheses. Common mistake is to do 240 divided by 2 times 3.14, and that gives the wrong answer because you end up multiplying by 3.14 rather than dividing it in the numbers here. We get 38.2 kilometers when done properly. And so that's our radius of the asteroid. There was one extra part of the problem which asked by how many times smaller or bigger than Earth's radius is the asteroid radius. The Earth radius is 6378. The asteroid is 38.2. So dividing, we get that they're different by a factor of 167. And of course, it's the Earth 167 times larger radius than that of the asteroid.